Okay, hello everyone. I can see that there are still some people joining, so we will wait for 2 or 3 minutes and then I can start. Okay, hello everyone. Welcome to this joint collaboration in our first webinar between Online Petroleum Academy and Petroleum Engineers Association. This webinar will be under the title of Fundamentals of 3D Modeling. So just before we start the webinar, I have a small presentation for 2 or 3 minutes, then we can start with the webinar. So I will be delivering just a quick OPA Make courses plan. I am Omar Hamid, business developer at OPA. First of all, as most of you know, or all of you know, that we initiated a collaboration between Online Petroleum Academy and Petroleum Engineers Association to facilitate the learning in the oil and gas industry and to give people as much knowledge as possible through our collaboration. And this webinar today is our first collaboration, and we expect to have a lot more to come in the future. So stay tuned by following our pages on our social media, OPA and PEA, on LinkedIn, Facebook, and all social media. So our first offer as OPA, so we have these recorded courses, 9 recorded courses. Each one of them is 15 hours, which include exercises and assignments. So you can buy these recorded courses. The price that's mentioned here is the price before the discount that I will mention later on. During these courses, you will have support from instructors. When you have any questions, you will also get a certificate of completion after you submit all your assignments. So OPA is making an aid offer, 75% discount, which will start today and will finish after a few days. So hurry up to get this offer as soon as possible. You can simply scan this code to register in the one of these recorded courses, or you can also fill in the link that my colleague will send in the chat right now. Okay, and our second offer is still going on, which is Ramadan offer for our upcoming course, Hydraulic Fracturing Using Fraccade, which is 40% discount from $250 to $149.99. So this is a 2 weeks course plus 1 week project. It will be between 35 and 40 hours of live training. In the course days, you will have 3 hours per day for 10 days. In the projects, you will have 1 to 2 hours per day for 5 days. There will be real case studies, full support from instructors to answer all your questions inside and outside the session. And of course, you will get a certificate at the end of the course to enhance and strengthen your CV. What will you learn in this course? Quickly, you will have 12 modules about the stimulation candidate selection, hydraulic fracture basic concepts, fracture modeling, basic geomechanics logs and interpretation, fracture software, fracture equipment, propment, hydraulic fracture fluids, diagnostic pumping interpretation, fracture treatment, pressure interpretation, fracture job QA/QC, post-fracture production. So at the end of this webinar, of this course in hydraulic fracturing using Fraccade, you will be a professional in the hydraulic fracturing from all of its sides. So this is the course plan or the course calendar. The green days are the course days, the blue ones are project days, and the orange ones are the break days. And if you are interested to join us, please scan this code to register in this course, or you can also fill in the link that my colleague will also send right now in the chat. Okay, and at the end, how to be an OPA ambassador. It's very simple. You just join us in one of our courses, whether it is a live course or recorded course. After that, you will be joining our OPA ambassadors group, in which you will get discounts on all courses in the future. You will also get group discounts in which you can invite your colleagues or your friends to join in the upcoming courses in the future. So join our 80 happy ambassadors and be part of OPA ambassadors group. And the rules for this webinar: please keep your microphone muted and camera closed during the webinar to avoid distraction for the instructor and for everyone. Put your questions in the chat box, and at the end, the instructor will answer them. Use your full name as written in the registration form in order to be able to take the attendance for you. So please, if right now you are using only the first name or using another name, please rename yourself to your full name, first name and last name, like you registered yourself in the registration form. For the certificates, they will be sent within 1 week from today, so don't worry. You don't have to send us emails or messages that we forgot you. We didn't. So after 1 week, we will send you the certificates. Don't worry. So thank you for listening to my presentation. And right now, I will introduce to you the instructor for this webinar. Mansour Khosravi is a petroleum geologist with more than 15 years of working experience at Illinois State Geological Survey in the United States. He completed his bachelor's degree from Shahid Shamran University of Ahvaz in Iran. Then he got his master's degree from Kharazmi University in Iran. So welcome, Engineer Masroor. You can share your screen and start your webinar. Mr. Mansour, we can't hear you. Maybe you're still muted.
Okay, great. Can you see my screen right now?
Yes, we can see it and we can hear you. You can start.
Okay, thank you. My name is Mansour Khosravi and I am reservoir geologist. I started my work, my career in Iran in one of the private oil companies. And on that time, I was a sedimentologist and help with actually reservoir modelers. After that, about 5 years, I was a well site geologist. I worked on offshore rigs on Persian Gulf, and I've been with Illinois State Geological Survey from 2014, but I work in the Illinois State Geological Survey. I work as a reservoir modeler. So in this presentation, I would like to actually give a summary about fundamental of reservoir modeling. Before that, today is Mother's Day in the US. So for the ladies in this presentation, I should say Happy Mother's Day. Okay, so at first for the workflow for creating a reservoir model is started from conceptual geologic model. It means that at first, as a reservoir modeler, you should know the concept of the pure geology of the area, of the field. For example, you should know what is the depositional environment on that area. And after that, you should know you should work with geophysicists because they prepare a horizon for you based on seismic data. Because all of the oil field are in subsurface, so you should know actually, you should have a knowledge about the field, the surface of the field, the faults, fault line, the displacement of the fault. And you should also work with petrophysicists. Why? Because they prepare you the logs, the petrophysical logs, for example, gamma ray. With gamma ray, you can find out the lithology of the reservoir. With porosity log, actually, you find out the porosity, the range of porosity for the cap rocks, for the reservoirs. And also after that, you must give a model to reservoir engineers, and they do actually the simulation, and after that they predict the reservoir behavior. So it's not the reservoir modeling is not just working with the software. You should know actually some sort of knowledge about the sedimentology, about the petrophysics, about the geophysics, and also dynamic modeling. So let's start with the depositional environment. And after that, we will look at other aspects of reservoir modeling. But at first, you should ask why we should use a 3D model. Why not a 2D model? Let me just go to, for example, actually the ultimate result of the reservoir modeling is finding the volume of the reservoir and also finding the porosity range of the reservoir. So in the past, for example, when I came to Illinois Geological Survey, I read several papers, and I find out that they didn't, for the past, for example, 40 years ago, they just use a 2D map, and after that, they just use an average phi or porosity, and after that, with A multiply, A is area of this, for example, reservoir or the field, to H, they find out, for example, the volume. After that, if they multiply it to phi, they can calculate the actually the pore volume, and with if they divide this one to BO or volume factor, they can find out the stacked tank oil volume in the reservoir. But why we use the 3D instead of 2D? Because in the 3D, we can easier find the special relation of the data. If you have a 3D model, you can find the trend of the porosity in different parts of the reservoir, not just in the 2D. In the 2D, for example, in the X and Y direction, you have another direction, that's a Z. So you can find out the relation of this data in the in a 3D model. And actually you can model the faults, because in the 2D, you couldn't be able to model the faults. And because some of the faults reduce the volume of the reservoir, some of the faults increase the volume of the faults. And you can also use the geostatistical algorithms and find the heterogeneity of the reservoir, not and after that you can give a better prediction of the porosity, permeability, and also water saturation. So also for the reservoir simulation, they can better history match the reservoir, and finally they could have a better prediction of the reservoir behavior. So if you look at this one, this is a stacked tank oil volume of the reservoir. You can see with this equation, we can calculate this number, okay? And A is area, H is the thickness of the reservoir, phi is the porosity, 1 minus water saturation divided by BO, that's a oil volume factor. So if we have these, as I mentioned here, we can, with the 2D map, we can calculate this one. But in the reality, we have a 3D model. So the 3D model give us a better prediction. Okay, let's start with the positional environment. Why the positional environment is important for us? Look at these two images, one of them for carbonate and one of them for turbidite. As a reservoir modeler, when you wanted to work when you wanted to create a model, at first you must ask yourself, what is the depositional environment? What is the conceptual geologic model of this reservoir? That's a carbonate or siliciclastic reservoir. For example, if it is carbonate, what is the deposition? You should ask sedimentologists, what is the depositional environment of this area? Look at this. For example, we say that this is the carbonate, but we have different type of carbonate. For example, we have in this depositional environment, we have some sort of reef. For example, in the Iran, we have osmari formation. Some part of that's one of the best actually reservoirs in Iran, and that's full of reefs. And the reef has very good porosity because of the fractures. So in this area, you can see that the energy actually in this area is high. Because of the high energy environment, we have some sort of porosity here. But in Iran, in the osmari formation, the fracture connect those porosity and the permeability is high also. So in this depositional environment, we don't have reef, we just have some patch reef. So in this depositional environment, reef is not very important, but this actually carbonate in the beach are very important for us because in this area, the energy is high and we have porosity here, but behind the reef, the porosity is not very high. In this area, actually we have shales. Shales has porosity, but because they are not the porosities, because the porosity are not connected, the permeability is low. So the sediments in this area are very important for us. But look at this turbidite environment or siliciclastic environment here. If we have turbidite, we know that actually in deep marine area, we don't have very good reservoirs. But if we have turbidites, we have some channels in this area, we have some slides and debris flow in this area because we have debris flow channels. So this area has a high porosity because the sediments, actually the source of sediments are in this high energy environment. So because of that, the porosity of the sediment in deep marine area actually is high. So when I was a well site geologist, we have oil field that was siliciclastic. And when they actually, when we drilled wells in some part, the production was not very good, but in some other parts, the production was very good. So actually, the sedimentologists interpreted that the positional environment of that area is turbidite. So because of that, if we hit these intervals, these sandstone or channels, the production was high. And if the well penetrate the shale sediment, the production was low. Look at these two different depositional environments. If we have mountain near the actually lakes or near the sea, we have some sort of sliding debris flow in this area. And if we have those type of sediments in this area, the porosity of those intervals is high. So they actually create reservoir for us. But look at this delta in this area. In the upper part, because they are near the source, near the mountains, or near the source of sediments, we have coarse-grained sediments in this area. And if we go toward the sea, the size of grain decreases. And also because the size decreases, we have shale in this area. So this part, the upper part, are more important for us. But in the fan delta, the sediments near actually the lake or the sea are very important. Look at this area, that's a reservoir. But here, the sediments in the upper part, in the upstream, are more important for us. At this fluvial or alluvial environment, in this area, because the sediments are near the source, near the mountains, we have coarse-grained sediments in this area. We have braided river. Also, we have meandering river in this area. We know that the braided river makes very good reservoir. Here, in the alluvial fan, they are not very good reservoir. Why? Because maybe in some part the porosity is high, but because we have the sorting is not very good. Because of that, the pores are not connected with each other. But toward in this area, we have some sort of quartz arenite, and the porosity are much better than this area. Toward the sea, because the grain sizes decrease, we don't have a very good reservoir in this area and also in this area. So because of this concept, the trend of the type of the depositional environment is very important for us. And also, I should mention that how we can use the data or the result of sedimentology in reservoir modeling. You should ask sedimentologists to prepare you some sort of map. For example, one conceptual map that shows we have, for example, alluvial fan in this area, braided river in this area, and etc. And after that, you should ask to prepare you the trend of porosity. Why the trend? For example, in this area, if we have an oil field or region that you wanted to study, in this region, why in this area the porosity is high? Why in this area porosity is low? You should ask this type of questions. And they will prepare you those map, and after that you can, when you wanted to model the porosity or permeability, you use those map as a trend, and you train your software to use those trends to give you a better result. Okay, the next step for a reservoir modeler, you should do the zonation. What is the zonation? The zonation is dividing the interval or the formation into different intervals, for example, with high porosity or high permeability, or without porosity or without permeability. So we have two types of zonation. One of them was traditional method that was based on just lithology, but in actually current time, most of the reservoir modeler use the sequence stratigraphy as a base for zonation. What is the difference of these two types of the zonation? Let me show you. Okay. In sequence stratigraphy, let me at first show you, maybe I can, if I just draw two, well, that's better. Okay, if we have, for example, two wells, well A and well B. Okay, we have, for example, high pru sandstone here. We have, that's a sandstone, and that's a shale. Again, that's a sandstone, that's a shale. If we have that sandstone here, shale here, sandstone here, and shale here. Okay, then when we use lithostratigraphy as a base for zonation, based on, for example, petrophysical logs, we say that in this part we have sandstone, we have shale here, we have again sandstone and shale here. So we connect the sandstone to each other, okay? That's shale, connect to shale, sandstone connect to sandstone, and shale again connect to shale. But the reality is not look like this. We have high porosity here in this area, low porosity, high porosity, and low porosity, okay? But the reality is not look like this. For example, if you look at an area with this depositional environment, you have, for example, a channel system here, that's a C, okay? We have a depositional environment look like this. That's a river, we have sandstone here, and we have shale in this area, okay? So sandstone in this part has high porosity, sandstone in this area has medium porosity, and the shale has no effective porosity. So in the same time, we have sandstone with high porosity, moderate porosity, and shale in a one actually area. So we must connect, but they actually create just one group. They are connected to each other. But look at this again, because this at first the sea level was here, but if the sea level goes down in this part, the sandstone shift toward the sea. And we have again sandstone in this part, shale in this part, okay? So we have another depositional or system track in this area. So in the reality, they are not look like this. For example, in the reality, the sandstone connect to shale, sandstone connect to shale, sandstone connect to shale in a big area, not just, I am just talking about, my discussion is about a regional system, not just a very small area, because in the small area, those sandstone are connected. But in a very big area, for example, in the US, in one state, you can see this type of sediments, for example, sandstone are connected to shale. So that's a new method. This one is a new method, and that was a traditional. In the traditional method, you can't you're not able to find the flow units because you you connect the intervals that in the reality are not connected. But if you use this one is based on sequence stratigraphy, and the sequence stratigraphy find those intervals that are connected to each other. So you can find this type of intervals. So that's a new method for finding for actually reservoir zonation. But in the small area, for example, if you have a small field, they look like this. You have, for example, 60 wells in this area. So you must connect those sandstone to each other. But in a state, in a big picture, you shouldn't actually connect those sandstone to each other. For example, if you have some wells in this area, you shouldn't actually connect the sandstone to sandstone. You should connect the shale to each other. Look at this one. This image is based on sequence stratigraphy, and you can see that it just connects some sandstone. For example, this sandstone with this sandstone. But based on lithostratigraphy, it just connects the sandstone with each other. For example, look at this one. We have sandstone here in this well, sandstone here with this well, in this well. It just connects the sandstone with each other. But in the reality, it looks like this. The sandstone are patchy. So it just, the sandstone in this part pinch out. We have some sort of shale here. So with the sequence stratigraphy, you can find those reservoir units. So for example, imagine that you drilled a well in this area. If you drilled a well in this area, so you can just actually penetrate this sandstone, and the production compared to this one, the production of this well is very low. Okay, if we wanted to have a quick actually summary about the sequence stratigraphy, the sequence stratigraphy is a branch of geology that study the intervals between two unconformity or between conformity or correlative conformity. What does it mean? Look at, let me show you with another actually drawing. If we have sea level here, and that's the land area, and this is the sea level. If in this area, if we have a river, we have erosion here, but we have the position of sediments in this area. So we don't have the position in this area. So those interval between that, so this one is correlative conformity. Correlative with what? Correlative with this unconformity. So the sequence stratigraphy actually study the sediments between unconformity or a correlative conformity. At first, because a slide actually in this state defined the sequences, major sequences. He defined the sequences based on major unconformity, and he actually divided the intervals in the US or in this state into 6 major sequences. But after that, in I think 1979, Whale and his colleagues just modified this definition, and they say that the sequences are between the major unconformities and also correlative conformities. So the relation of this interval with these surfaces are very important for us because they show us the direction of the beds and also the stacking pattern of the sediments. And for example, as a geophysicist, they study these terminations, and after that, they find those intervals and they shows us a large picture about the conceptual model of the reservoir or about the area. Okay, if you look at this is the stacking pattern of the sediment. For example, this is the transgressive system, right? I will show you with better images or better drawing in the next slide, what is the accommodation space? When we say that because the sequence stratigraphy is very dependent to accommodation space, actually the area between the sea surface or the surface of the sea and also the bottom is the accommodation surface is very important for us, because when we have accommodation surface, we can have a depositional of sediments. And the sequences or stacking pattern are very relative to this accommodation surface and also rising or falling of the relative sea level. I will show you in this actually with some drawing. It's much better if I show you those. Okay, look at this shelf system. If we have, for example, the position, sea level is here. Imagine that sea level is here at the step 1, and we have the position. So because of the deposition accommodation space, at first we have this accommodation surface, but because the sea level is here, with the position, the accommodation space reducing, okay? And in this area, when we have, for example, we have a river system that deposit the sediments here. So because of that, the accommodation is reducing. So in this area, because we don't have accommodation, actually the sediments goes in this area, right? Because they go up, the sediment go in this direction. So actually the sediments, we have, for example, sandstone here. The sandstone goes toward the sea. Because of that, look at this image. This is progradational stacking pattern. And at first we have this accommodation. So we have the deposition in this area. With the position, with the continuous deposition, the accommodation space reducing. So we have a movement of, assume that they are sandstone. So the sandstone actually goes toward the sea. So the direction of the sandstone are toward the sea. But look at this one. If with actually the position of sediments, the sea level goes up. So the river retrograde, and we have transgressive system track. So after that, after a huge transgressive system, we have maximum floating surface over this area. So in this area, we have shale. most of the time we have source rock with the transgressive system tract or with maximum floating surface. And in some part, when we have actually deposition of sediments, also the accommodation goes down. We have reducing or decreasing of accommodation surface because of the flux of the river. But assume that sea level goes up in one area because of some of the cycles for, that we have some sort of cycles for sea level, relative sea level. In, for example, some area we have a low actually relative sea level. We have in some time we have high level of sea level. So if we have the sea level goes up, and because of the flux we have actually flux of river, and we have low accommodation surface, the sediments deposited on top of each other. So we say that we have aggregational system tract or stacking pattern. And they are important for us because they shows us the thickness of the reservoir. They shows us the type of reservoir, for example, or source rock, for example, in the maximum floating surface, because the sea level goes up suddenly and the shales cover the sandstone. So we have source rock. In this part, because of the keep up of the sediments with relative sea level, we have a huge reservoirs. In this part, we have a trend of the reservoir toward the sea. So they are important for us because they shows us the trend. I emphasize on the trend because that's very important for us as a reservoir modeler. Okay, as I mentioned that we have two types of zonation. One type is based on lithostratigraphy. You see that we have 3 wells. We have shale, we connected just the shale with each other. We connected the sandstone with each other, and etc. We have another type of reservoir zonation is based on sequences or system tracks. So you can see that they are not continuous. We have some shale loops, we have some patches of sandstone, and this type of zonation gives us a better prediction. Look at this one. This zonation was based on sequences stratigraphy. You can see they are not continuous. They are just patchy. For example, this sandstone pinch out in this area, and if we drill a well in this area, we can just hit the shells without the sandstone. And this is the 2D image of the flow units. This part are the flow units of us. If we have a zonation just based on lithostratigraphy, we must actually connect this interval together, and we were overestimate. We will overestimate the porosity. Sometimes we underestimate the porosity. Look at, for example, if we have an oil field, look like this, and we drilled a free well in this area, and we hit just the shales in this area. And the sedimentologist or someone that just look at the wells just based on stratigraphy, it connected those intervals to each other, and he mentioned that we have just shale here and the reservoir quality is not good. But if this interpretation is based on sequence stratigraphy, they can find some patchy, for example, sandstone here, some patchy sandstone here, and they say that because of the sequence stratigraphy, you can drill a well in this area and penetrate the sandstone with high quality. Okay, again, that's the flow units based on the sequence stratigraphy. One other thing that is important for a reservoir modeler is diagenesis. What is the diagenesis? Diagenesis is physical and chemical changes that alter the sediments after the deposition. Some of the diagenesis processes are very important for us. For example, dissolution, compaction, cementation, and dolomitization. Why? Because they can create or increase the porosity, or they can reduce the porosity. For example, cementation can reduce the porosity. Dolomitization can increase the porosity. Dissolution can create some pores for us that are important for us as a reservoir modeler. Look at this type of dissolution. That in the carbonate, we have this type of porosities, for example, interparticle, intraparticle, intercrystalline, moldic, fenestral, Schilter, and growth framework. But if you look at this area, they are fabric selective. What does it mean? They are just hit the fabric. For example, we have an aluchem or we have a grain. We have some sort of porosity here, but they are connected. No, they are not connected. If we have some sort of fracture here, they can connect this porosity. This type of porosity are more important for us because they are connected porosity. For this one, maybe we have 20% porosity, but the permeability is low, maybe less than 10 millidarcy, or maybe less than 2 millidarcy. But in this area, we have, in the same time, we have porosity and permeability because they are connected to each other. They are not fabric selective. It means that it affected this type of porosity. It affected the matrix and also the grains. And that in the carbonate, this is one of the important type of porosity channels. They are larger than WOGs, fractures, and cavernous porosity. But one of the other porosity that are very important for us is this one, intercrystalline porosity. In this actually fabric selective porosity, the porosity are connected. We have this type of porosity in dolomites, and because we know that when most of the dolomite are secondary dolomites, and the dolomite converted from the calcite or aragonite. So when we have a conversion of those minerals, actually the volume, when, for example, if we have a calcite and it converts to dolomite, it reduces the volume. And most of the geologists say that we have about 12% reduction in volume. And when you have a reduction in volume, so this volume that disappeared, it actually create a porosity. So the dolomitization is very important for us because we have reduction in volume and it creates a porosity. and they are connected to each other. One important porosity in siliciclastic sediment is intergranular porosity. So we have some, for example, quartz, and between them we have porosity, and we name it the intergranular porosity. So look at this type of, for example, diagenetic cementation. In the cementation process, or we have precipitation of the, for example, calcite, quartz cement between the grains. Because of that, we have a reduction in the porosity. That's an O8 grain stone. That's one of the carbonate. Most of the time when we say, because these O8s are created in high energy environments, we should expect high porosity. But because of the cementation in this part, you can see that this type of cementation in this part, the porosity reduces. So we have low porosity for this sandstone. Look at this sandstone. We have quartz grains. We have some sort of feldspars, and you can see we have a calcite cement between the grains. So because of that, we have no good porosity or reservoir quality. But look at these crystals of dolomite. Look at these rhombs of dolomites here, and in this area we can see very large, actually, porosity. But look at this, they are not connected to each other. They are not connected, for example, to this pore in this area. But in some part we have those connections. If we have, because the dolomite is more fragile than calcite, most of the time we have some sort of microfracture or fracture for dolomites, and because of that they connected the porosity together. And look at this quartz arenite. You can see we have a connected porosity together. And that's intercrystalline and moldic. We have some moldic porosity in this area, and we have intercrystalline porosity. Because of these porosities, they are connected to each other. And we have, if you look at this bioclast, we have some sort of vaggy porosity here or here, and but most of this porosity are connected to each other. So they are vag. In this part we have vags, because actually the dissolution affected both matrix and also the grains. That's the grains, and that one was matrix. But for this part, that's a moldic porosity, because it just affected the grains. One of the diagenetic processes is compaction. Compaction is important because it reduces the porosity, and in some part, because of the dissolution or chemical dissolution, we have a precipitation of the also the cements on other parts. So we have low porosity. One of the things that show us that we have compaction is stylolites. If we in some cores we can see the stylolites, and also in the thin section we can see those type of geologic features And based on that, we can say we have a compaction. Because of the compaction, for this interval, we don't have a good reservoir quality. Okay, let's right now let's look at or let's have a brief discussion about the type of map we used in reservoir modeling. Some of we have different type of maps. Some of them I mentioned here, same as a structure map, thickness map, same as isopac map and isocore, porosity and permeability map, deep azimuth and deep angle maps, and also trend map. As I mentioned in the previous section, we use some sort of trend map that comes from interpretation by sedimentologists, because those maps shows the trend of porosity and permeability. What is the structure map? Structure map, actually, that's the kind of subsurface map that shows the elevation of the reservoir. And you can see that in this, in those type of map, you see that the elevation always mentioned as a minus, as a negative actually number. Why? Because it's on the subsurface. We use the positive numbers for the area above the surface and negative for above below the surface. And this depth is based on the TVD subsea. And in this map, I show what is the type of depth we use. When you work as a well site geologist, they give you a depth, or the depth to you as an MD, or measure depth. They call it driller depth or measure depth because I see them. Look at this well here. They actually measure the depth from Kelly bushing or rig floor to the actually reservoir or to the depth. So when it hits the interval, they give you one depth. That's a measure depth or driller depth. Another depth they give you, that's a true vertical depth. It means that vertical depth from the Kelly bushing to the interval. Another depth is based on TVD subsea, based on sea level, that the reference is the same for all of the depth. Why? Because it's based on the sea level, the elevation of the sea level. So if you look at this is the TVD subsea, the depth of the intervals to actually the mean sea level. So why? The structure map is based on, it will create based on this depth. So if you wanted to prepare a structure map, you must know the elevation or mean sea level, or elevation of this one, elevation or mean sea level. And after that, they can create, because it has a reference. But imagine that you have a hill here. So if you wanted to use a TVD, assume that this is a vertical line, that's a TVD, and that's the measure depth. But imagine that if you compare these depths, these TVDs with these TVDs, they are totally different, because the reference is just the Kelly bushing or rig floor. But here, the reference is the same for everything. You have the mean sea level for every depth. So the elevation of this one, for example, this one is 800. Here is 600. If you subtract the TVD to this one or this one, because you have the same reference, now you can compare the depth. But with these two depth, you can't compare because you don't have the same reference. The reference of this one is rig floor, this one is rig floor, but different. It has the different depth. But for this one, you have a date. You have the same date. Okay, so after that, you must prepare the thickness map. For the thickness map, you can prepare two types of thickness map. One of them is isopack and one of them is isocore. What is the difference of them? The isocore, actually, the vertical is the vertical thickness of the interval. Look at this one, for example, from here to here is vertical thickness. And the isopack is the stratigraphic thickness. In all of the location, this one is the same because it actually compare the stratigraphic thickness. Imagine that you have a anticline look like this, okay? And you have a deviated well. You penetrate a deviated well in this area, okay? So what is the true vertical thickness? True vertical thickness is in this area is this one, in this area in this one, and in this area is this one. What is the measured depth? Measured thickness, that's the measured thickness of this interval. If you don't apply the actually the angle of this interval, and you just say that, for example, you have, because the petrophysical laws are based on measured depth, you can see, if imagine that this is, assume that this is sandstone, all of them is sandstone, and the petrophysicist gives you a log, and you see that you have a, for example, sandstone with high thickness in this area. So you said, wow, I have a very, I have an interval with very high porosity and the thickness is 100, for example, meter. But in the reality, because that's a deviated and well penetrated the flank of the anticline, that's not the thickness. You must actually import the survey of the well because it mentioned the deviation of the well, the azimuth of the well, and also you have the horizons. For example, in the software, you have the horizons. So you have the deep angle, deep azimuth of the horizon, and after that, you calculate the isocore and also isopack. Because of that, so this is the true vertical thickness. This is the true vertical thickness, but actually the real thickness is a stratigraphic thickness. In the crust of the anticline, the true vertical thickness, this one is equals to this one because both are the same. But in this area, the true vertical thickness is higher than actually true stratigraphic thickness. So that this one is the isopack are more important for us than isocore. In the Petrel software, you can see just isocore, but in the reality, that's the isopack, because you give the Petrel software the horizons, also the direction of the well, and it calculates the true stratigraphic thickness for you, not just the true vertical. So, and I've saw some spreadsheet in Excel then calculate the true stratigraphic thickness from the based on the well formation, for example, survey, and the dip and azimuth of the horizons. Okay, after that, you must prepare based on the zonation, as I mentioned in the previous sections, you must prepare a thickness map. Thickness map for each zone. For each zone, you prepare a thickness map or an isopack map, and after that, that's okay. Sorry, I will talk about this thickness map in the next slides. But let's look at this porosity map. This porosity map also prepared based on the average porosity of the intervals. You can have different wells with different porosity, and after that, you based on those points or those intervals, you can prepare some sort of porosity maps or permeability maps. Another type of map are the deep angle and deep azimuth maps. If we have some sort of intervals, for example, here, and if we have a horizontal surface, the intersect between the horizon, those horizon and the intervals, actually the angle between those horizon surface and the interval is the dip. And this intersect, also the direction of this intersect shows you the azimuth of the interval. They are very important for us because they show us some sort of geologic feature. I show you in this structure map. That's a structure map based on TVD subsea. And look at this deep angle. And look at this area with high angle. It mentioned that in this area, we have intervals with high angle. And maybe that's a fault, or maybe that's a monocline, but the deep of the interval are high. Look at this area. We have so many faults. That's a map of Illinois. That's the structure map of one of the formation in Illinois. But look at these areas here with high, actually with warm colors. We have so many faults in here. So with this deep angle map, you can find those faults or structural feature. Also with this deep azimuth, it mentioned that in this area, because we have warmer color, the direction or the azimuth are very different with this area. So maybe we have, we can tell two stories for this area because they have different deep azimuth. Okay, right now we wanted to actually, we have the data of the positional model or the trends. We do the zonation. We prepare some sort of 2D maps or 3D maps, for example, horizons, and also some sort of deep azimuth deep angle maps. And right now we wanted to create a 3D model. We wanted to distribute the properties after that with those 3D models. And what is the steps for creating a 3D model? The first step is creating a stratigraphic framework for the reservoir. After that, we create a structural model. And if we have the data of seismic or the data of the sedimentology, we can prepare a facies model. And finally, we will do the property model and model the porosity, permeability, water saturation. So for creating a stratigraphic framework, we must have actually the horizon from seismic data. Or sometimes you don't have seismic data or horizon from seismic data. Well data because you have the depth of penetration. For each formation, you can create a horizon for that interval. That's one of the horizon. When you have a horizon for one of the formation from, for example, seismic, we call it interpreted formation or interpreted surface. But you don't have, for all of the formation, you don't have the horizon for seismic data because of the, for example, low quality of reflection, low quality of, or low resolution of the seismic data. So you must calculate other horizon. So we call other the calculated horizon or calculated surfaces. We have two types of, when you wanted to have the horizon from seismic data, maybe you have the 3D seismic data or 2D seismic data. For exploration, mostly you have the 2D seismic data because they are less expensive than the 3D seismic data, and they just give you a very low actually data from the horizon. They gave you actually the type of horizon, but for example, for the faults, fault line, fault displacement, they are not have a good quality. But for 3D, but when you have a field, developing field, mostly you have the 3D seismic data, and the 3D seismic data are very expensive, and also they give you a better perspective of the reservoir. For 2D seismic data, you have just some lines. For example, if you look at this track here, you have some geophones in one line, and after that they send a sound, and based on the reflection, they give you some sort of horizon, the depth of the horizon. But for the 3D, they have different lines, and they send a sound, and after that they receive the sounds, the reflection with different geophones in different part of the area, and after that they interpreted that, and they can give you the type of faults, surfaces, which horizon affected by faults, which of them are not affected. So they have more data than 2D seismic data. Look at this line of 2D sizing. Assume that we have this line. They give you just the type of actually the depth of the horizon and very low information about the, for example, geobodies. But for 3D, they can give you the geobodies that actually, if they have a good interpretation, they can give you the 3D of the geobodies, channels, and etc. Okay, when a geophysicist gives you the interpreted horizon, for example, this one, you must actually calculate other surfaces. So assume that geophysicist gives you 2 surfaces. So after that, if you have other formation between them, you must calculate those. How you calculate those? Based on the information of well tops and also with the interpretation of the sedimentology and also with the isopack maps or isocore maps that you created. Because if you have isopack maps, you can calculate the thickness of the intervals between the horizons. Okay, this slide shows that if you don't have the isopack map in some part, software couldn't actually find the exact depth. But if you have the isopack, for example, this one, it has isopack, it created the other surfaces. And that's one of the, for example, that's one of the other column that you can actually find the thickness between the 2 intervals based on the isopack maps. Okay, right now you create a stratigraphic framework of the reservoir. It means that you create a horizon with horizon zones, subzones, and after that you must import the faults. You must import the fault lines, displacement. You can import the faults or displacement of the faults in 2 ways. One of them by actually interpretation of the well log data. For example, you can find a fault in one well and you study a nearby well and you couldn't find that fault on that well. Let me show you, for example, where is my mouse? Okay, let's think about that. You have 2 wells. One well in this part. You have, for example, shale here, you have sandstone here, you have again shale here, okay? You have that shale, that sandstone, that shale. But you have another well here. You have shale, you have sandstone, you have again shale. So based on a structural study, you can find that this actually reducing in the thickness of the interval is based on a fault. So you interpreted that you have a fault here because the thickness decreases, or sometimes because of the trusty fault, you have the repetition of the interval. For example, you have a shell here. Again, you have this shell, repetition of this shell again. Imagine that you have a trusty fault. That's a fault. Yes, that's the trusty fault. And you have a well here. That's just one interval, right? This interval 1 is one interval, but you hit that, you penetrate this interval 2 times. So you have this interval and this interval again. So in the actually in the area without fault, it's look like this. Okay. But in area, you have the repetition of this interval. So based on those, you can interpret it that you have a fault. And most of the time, the geophysicist gives you the polygons of the faults or fault surfaces or fault lines, and you can import those feature into your reservoir modeling software, same as RMS, same as Petrel, and after that do the structural modeling. And they are very important for you because they can reduce or increase the volume of the reservoir. Okay, as I mentioned that that's the result of one of the fault study or structural modeling, and the geophysicist actually gives us the faults, and we imported those faults. You can see the affection of those faults on surfaces. You can see some sort of displacement on surfaces. And after that, you must construct a structural framework. It means that you must, based on those interpretation, you must know that which surface affected by faults, which surface didn't affected by faults, and you, for example, you can't see any faults on that surface. In this surface, as you see, you have some sort of displacement. Maybe in this part, you have more displacement compared to this actually surface. After that, right now you have in this step, you have the structural framework. But right after this step, you must actually apply the porosity, the permeability, water saturation to this interval. But you can't do that because you don't have any cell. You must actually divide this horizon, divide this interval into the cells. Why? Because you wanted to create a numerical model. If instead of this surface, you have the cells, you can apply to each cell, to every cell, each individual cell, one number. So based on those numbers, you can do the geostatistical modeling, or you can find the trends of the porosity. But with this is this structural modeling, stratigraphic modeling, they are the first step. You just create a framework of the reservoir. After that, you divide those into grids or cells, and you assign the numbers, based on porosity and permeability, and populate the reservoir quality. Okay, for creating grids, we use the pillar gridding that create a skeleton for the reservoir, and it creates the grids. And in this step, you can actually divide the surfaces or layers into the grids. If you sometimes you heard that you have a fine grid or coarse grid. What is the difference? When you, for example, if I have a surface, look at this one, assume that this is the one of the horizon, you can actually, in the X and Y, it means this surface, not Z, you can divide them into grids, and each grids, and also in the vertical section, you can divide them into different layers. So you have a cubes of cells, right? You have a cube for each of them, same as this. You have a different cells. In if you have very coarse, or you increase the dimension of the cells, you have a coarse grid. But as a reservoir modeler or geologist, you wanted to see all of the geologic features. So most of the time, geologists or reservoir modelers create a very fine grid to see all of the geologic features. And after that, they give this fine grids to reservoir engineers, but they have a limitation for working with these fine grids, because they actually, because of the time of the simulation or the time of the runs, they wanted to have they wanted to work with very coarse grids. For example, they can work with models over 5 million cells, but most of the time, you in the reservoir geology section, you create a fine grid with over, for example, 30 million cells. They reduce the cells. They reduce they increase the dimension of the cells, and after that they run the model. We know that because of those coarsening processes, they actually eliminate some of the geologic features. But as a reservoir modeler, you should help them to avoid those type of elimination that affected the reservoir part and very important geologic features. So in the pillar grading process, you divided the reservoir volume into the cells or into the grids. And most of the time, as I mentioned, that you create a fine grid. That's the pillar grading process for a reservoir. It creates a skeleton from the top to base. It isn't based on the horizon. It just creates in the petrel. It creates a skeleton from the top to base of the reservoir, and it's a middle part of the reservoir. After that, after this process, when you have a reservoir, for example, you divided the reservoir into the cells, and you have a well, right? You have a well, and you have the for example, half meter data of the wells, but you have for example, 2 feet or 2 meter thickness of each grids, but you have different, based on the logs, you have different data. For example, if this is 2 feet interval and the data of the log are half a feet. So you must average those data and assign just value to each cell. And we done this process in a scale-up process. And in the scale-up process, look at this one. We assign for this, that's the porosity log. And for this interval, we just assign one value to one cell. And we mentioned this process, a scale-up data. So you have, for example, 60 well in an oil field. After that, you have for those well, you have porosity data. Assume that's the field. You have 30, for example, well in different part of this field, and you have the porosity logs. So for each of these logs, you and you have the grids also. So you do the scale-up process. You assign one value to each cell. So you have the scale-up data for these 60 well in different area. But how about this area without the data? You have just the data, scale-up data of these areas, right? So for calculating those, you must do the geostatistical processing or algorithms and distribute the properties, and I will show you in next slide. One of the other aspects for reservoir modeling is facies modeling. If you have the data of, for example, 3D seismic data, you can find the trend of them, for example, channels. So with those, actually, it for volumetric, not directly, you can use the facies model. You indirectly use that one. How? You can train your, for example, porosity model. If assume that this is the channel, you train the porosity model or co-create the porosity model with facies model. So based on that, you can find the trend, and that's actually the trend. The facies is the trend. The porosity uses this trend to distribute the property. So based on that, it doesn't distribute very high porosity in this area. But most of the time, you don't have the facies model. So you must use this one. They call it a pixel-based model. This is object-based because you have the object of the, for example, channel. But if you don't, you do this process. This is the pixel-based. It doesn't have the quality of this one, but based on the geostatistical algorithm, it shows that it has a high quality. Okay, so in the next step, as I showed you in this part, you have the scale-up data for some of the wells, but you must distribute the properties between them. How you can do that? You must know some geostatistical aspect or geostatistical knowledge about. You must have some geostatistical knowledge to do that. And in the petrol or in the RMS, you can do that. You can do that based on variograms. The variograms showed you and calculate the variability of the reservoir. This is a channel. This is a channel. And if you look at this one, you see that we have sandstone here and also we have sandstone here. So variability in this direction is low. It means that we have similarity of the type of sediments in this direction. But how about this part? We have shale here, we have sandstone here. So the variability in this part is low. This direction that shows the variability in higher range is major variogram or major range. This direction shows the minor range because the similarity of the range of the similarity is low. So it shows the minor range. And also in the 3D, you have another direction is the similarity based on depth, right? And this is the vertical range. All of the variograms, look at this one, all of the variogram is based on these three major and minor range. So if you have, for example, a well in this area, based on variogram study, you can find the range. Where is the, for example, what is this distance with similarity? For example, similarity in this direction maybe is, for example, 2000 meters, right? And in this direction, the similarity is, for example, 500 meters. And in vertical, we have, for example, 5 meters with similarity. So based on these variograms for each zone, you do the variogram study for each zone. For example, you have zone A, zone B, you create a variograms in the petrel in 3 direction for each interval. And after that, based on those ranges, you can simulate the porosity and distribute the porosity or permeability. So that's I don't want to actually mention this slide. Just there are type of variograms how we can find the major and minor ranges. For example, in this variogram that study, that's a seal. It means that in this part, in this area, in this range, the sediments are actually similar, but toward this area, they're not. They don't show similarity. Based on those graphs, we can find a range, and we use this range. For example, we use this range, vertical range, minor range, major range. We can distribute the properties. Okay, right now, I want to just mention that we have two types of simulation. One of them is based on a stochastic, and one of them based on deterministic. If we have an oil field with many wells, and we have so many data, okay? So we can, because we have more, very high information about this field, we can use the deterministic model, and it creates us a very smooth maps, and you can actually predict the behavior of reservoir. But assume that you don't have so many wells. So you must randomly distribute the properties. And if you use this deterministic method, because it just honors the data of the well. So it creates a very smooth. Sometimes look at this one. That's a this one. The blue curve is reality, but for this one is based on Kriging or deterministic. It underestimate or overestimate how the properties. For example, you have shale here with low reservoir quality in some of the wells. So it underestimates the properties if you use the smooth map. If you have, in these wells, you have, for example, sandstone, it because it just same as lithostratigraphic zonation, it connects the shales and gives you very smooth maps. It overestimates the porosity, but with using different realizations in the stochastic simulation model, it randomly distributes the properties and it gives you not one result, several results, but the uncertainties is lower compared to deterministic model. Okay, as I mentioned that the ultimate result of your model will be having a volume of the reservoir, volume of the oil, volume of the gas. So as I mentioned in the first or second slide, with the 2D, you can find the volume by multiplying area on to thickness. That's the thickness or isopac. For example, you have a field, you have the area, and after that, you can find the volume. But in the 3D model, you have a 3D, a special relation of those, and you can actually, you have the area, you have the thickness based on those maps, but in 3D, you have also the phi, and you can actually calculate the what the pore volume, and after that you have the water saturation. You can and also based on the well test, you have the the volume factor, and in a result you can actually have a better prediction and find out the stack tank oil in place of the reservoir. But this one is in 3D. That's a phi model. That's an isopac map. That's 3D volume of the reservoir. So it gives you better prediction of the reservoir behavior. In the petrol, you have this formula in the volumetric section. For example, let me at first just mention that if you have for example, a reservoir, you have sandstone in this reservoir, but some part of this reservoir has high porosity, for example, over 15 porosity, some of them not, about, for example, 10%. Here is 20%. Sometimes you must actually have a cutoff to eliminate those intervals with low porosity in a reservoir and calculate the net thickness. For example, you have the thickness of this part, you have the thickness of this part with high porosity, thickness of this part with high porosity, and this is low porosity. So you have the thickness of total thickness of the reservoir if you just divide the net thickness or net pay thickness to total thickness. This actually shows you the ratio that we call it net to gross. So net to gross is very important because it shows us the net thickness of the reservoir. Maybe you have 100 feet of interval that we call it reservoir, but just about 70 feet of this reservoir is net. It has over, for example, 10% porosity. So for some of the calculation, we need that. For example, if we wanted to find the net volume of the reservoir, we have the bulk volume. As I mentioned, that area multiplied to the edge thickness, we have the bulk volume. If we multiply to net to gross, it gives you the net volume. Pore volume is net volume, this one, to porosity. And this is hydrocarbon porosity. Pore volume, you have the pore volume here, to oil saturation, and etc. And finally, you can do the volumetric equation and find out the stack tank oil in place of the reservoir. And if you have the recovery factor, for example, you can recover 100% of the oil in the reservoir. You can just recover maximum 25 or 30% of the reservoir. So if you multiply the stack tank oil in place to recovery factor, you can say that what's the recoverable oil from this reservoir. Okay, that's all on my slides. And I don't know, we have time for the question or not. Thank you so much.
Thank you, sir. And thank you, participants from the whole team of PE and OPA. And sir, yeah, we have got some questions or queries. You can see the chat box, and also I will say for you, like the first question, how we do this analysis by 3D view rather than 2D?
Why we do the 3D rather than 2D? That's a question.
Yes, sir.
Yeah, actually, as I mentioned in these slides, let me go over again to this slide. When you do the 2D, for example, that with 2D just you can calculate the volume of the reservoir roughly. For example, you can say that in this part of in the 3D, you can say that in this part, let me change it to again to pointer or laser pointer. Oops, sorry. To pen. Okay. In the 2D, you can say that, for example, I have the area is the same. You have the isopac map is the same, but how about the phi, or how about the porosity? In the 2D, when you wanted to calculate that, you just roughly say that in this reservoir, we have 20% porosity. So the calculation is based on that, A to H to phi, okay, 20%. But in the reality, it's not same as this. In the reality, when you create a heterogeneous reservoir, you say that in this part we have 20%, in this part we have 10%, in this part we have 15%. So based on that, based on those actually trend of the porosity, based on those different porosity in different area, it calculate the volume or net volume of the reservoir. Yes, that's one part. Another part is the faults. You in the 2D, you can't actually import the faults and calculate the exact volume of the reservoir. But in the 3D, you can do the structural modeling. As I mentioned that, for example, you have a fault in this area, you have a trusty fault in this area. So you have a well here, right? And this is sandstone, this is sandstone. You hit the sandstone 2 times. So the volume of the reservoir increases, right? But you have a normal fault here. And you go in this part, that's a sandstone again. And you don't actually hit this, penetrate this sandstone. So it reduces the volume of the reservoir. So you can't actually do the structural modeling in the 3D, in the 2D, but you can do that in the 3D. Yeah. Nothing.
Okay. Now we have some questions. First question, what are the reasons behind some areas being low porosity and others high porosity?
Why in some area we have low porosity? That depends on, at first it depends on the dissolution, the diagenetic process, especially, let me just show you. Okay, the first thing is related to energy of the environment. For example, in this area, if we have high energy in this area, because of the, for example, the wave, they actually clean those matrix between the grains. So you have the porosity in this area, but in this area, nothing clean the well. Some of them is related to participation of other minerals. For example, if we have a if we have a very warm and warm environment, warm and dry environment, we have a cementation of anhydride between the grains. Because of that, it decreases the porosity. Sometimes it related to the porosity has a relation with the source of the rocks. For example, this part, the source of the rock, we have a matrix between the grains. We have grains here, but we have matrix between the grains. So we don't have porosity. But in this area, because of the high energy environment, there is no matrix between the grain. Because of that, we have high porosity. So in different part of the depositional environment, we have different type of porosity. Because of that, I mentioned in this slide that finding the depositional environment is very important for us. Sometimes we have the solution of, for example, if we have an area with the solution, the water between them actually dissolve the ions, and it contains the ions, and it goes to other area. It participated on the cement between the grains, and because of those cementation, we don't have porosity. sometimes it's because of the compaction. For example, you have some interval, but you have the compaction. At first, in this area, you have deposition, and maybe you have 10% porosity. But because of the pressure of the overburden pressures of the other sediments, you have the compaction. Because of that, the porosity reduces. So the diagenetic processes are very important because they showed us why in this area we have porosity, why in other area we don't have porosity. Yeah.
Okay. Now another question. What is the main considerations in order to get a consistent distribution of water saturation in modeling?
Sorry, I can't hear you very well. Can you repeat it?
Okay. What is the main considerations in order to get a consistent distribution of water saturation in modeling?
For water saturation, most of the time the petrophysicist must actually interpret the log data. They have resistivity log data. So based on that, they can prepare and they can also calculate the water saturation in other areas, and with some of the well tests. You can find the current oil in place of the reservoir. So if you have those, for example, resistivity logs, interpretation of those, and the type of fluids between the grains, you can, or petrophysicists can give you the water saturation. And based on that, you can model that. You can model the water oil content. I think I have it in the last slide. Yeah, and after that, in this process, you have them based on those. You can based on some test or based on the percentage of water between the grains, you can find out the location of the water oil contact. That's important for you in this image. For example, that's a oil water contact. And based on that, you can say that this is the net volume of us, because we have the porosity here, but this porosity occupied by the water, by the salt water. So you must eliminate those volume, and after that you calculate this volume of the reservoir. So the water oil contact comes from two other sources. One of them is resistivity logs, and one of them is well test. So, and in the petrol you can model that. Yeah.
Okay, great. Another question. How do you apply well testing to calibrate your static modeling in terms of connectivity and permeability distribution?
Yes, exactly. The well test, because you don't have the permeability data, right? And most of the time you don't have so many permeability data. You must actually predict the permeability based on some well test and also the porosity data and some interpretation. So the well test help you to calibrate, because in the well test you have just some data for some of the interval, very few data for some of the intervals. And based on that, you can calibrate the permeability data. Because most of the time, just based on porosity or based on the logs, it's very difficult to actually model the permeability. What helps you that is core analysis. One of the main things is core analysis that gives you the result of porosity versus permeability, or finding the rock types interpretation based on those. And one of the other things is well test. Yeah.
Okay. Now another question. If you required to model the permeability, what are the different or best options utilized in your opinion?
For me is at first, actually I work with porosity and also well test for predicting the permeability. The best way to predict, if you have core data, I think it's the best way is at first you create a log based on core data. You have, for example, 20, 30, 40 data of cores for reservoir in one well. You can model that, and based on that, you predict the permeability based on porosity and calibrate that with the core data. Calibrate those two logs, that logs that comes from the core data and the logs that just calculation. After that, if you have well test, you can calibrate that based on well test as well. So if you have those, the prediction is very similar. I mean that geostatistical algorithms, just averaging method is a bit different. For example, for KH, we use the arithmetic or geometric averaging method for the permeability, but for porosity, we just use the arithmetic. But for KZ, we just use the harmonic averaging method. But other aspects are the same. The finding the variograms is the same in both, and distributing the property are the same. But the difference is just calibration. Calibration, I think, is the most important thing for modeling the permeability.
Okay. Now another question. Which type of environment is the best for producing carbonate?
Yeah, that's a good question, but actually that's different. For example, as I showed you, we have different type of depositional environment. We have channel system, we have beach system, we have barrier system. They are very important in carbonates. You can say that this one, if we have them, for example, barrier system is more important than turbidites. We have so many, for example, in the carbonates, instead of turbidites, we say that calciturbidites, but they are totally different with each other. But you can't say that, for example, if we have a barrier system, this is much better, the reservoir quality is much better than, for example, reef system. Maybe you have on that area, you have, for example, fracturing system that connect the pores, and in the reef system, the quality is better than barrier system. So you can't exactly say that in which system has the highest, but I can say that, for example, in beach system, in a barrier system, in a reef system, or in a channel system, the quality are very good.
Okay, thank you. Another question. How important topographic survey is to understand subsurface importance before conducting geophysical survey?
That's very important to find out the topography. You have the topography. You have the topography, and at first, when they wanted to actually do the geophysical survey, they have the topography. They use those surfaces to find out the thickness of the actually surface formation, and after that do that. So that's very important for you, and that's the initial step for doing this job.
Okay, one last question. What is the impact of the algorithms for modeling heterogeneity in fluid flows?
That's a good question. Yeah, it has very high impact. It has very high impact using the different algorithms. For example, for kriging, as I mentioned that in the deterministic slide, for the wells that are very close to each other. For example, let me just mention one example. We had 4 wells in one oil field that we use those wells for CO2 sequestration, and we wanted to actually have we wanted to distribute the properties. So we use but those 4 wells are very close to each other. The distance of those 4 wells was about 1,000 feet. It's around 300 meter away from each other. So we use at first we use the stochastic modeling. Stochastic modeling works very well for wells that are very far from each other. But when your wells are close to each other, because they are very close and the reservoir quality are very same, it's better to use the deterministics, and the deterministic gives you a better result. But if you have a very low number of wells in different parts and they are far from each other, it's better to use the stochastical algorithms or stochastic algorithms, because it randomly distributes the properties that gives you a better result compared to deterministic. Deterministic overestimate or underestimate the porosity or permeability in most of the areas.
Thank you, Engineer Mansour. We are pleased that you joined us today in this webinar. Thank you for your awesome presentation and your outstanding efforts. Please, everyone, you will find the link to the feedback form in the chat. Please fill it so that we can get better, and we will see you in upcoming webinars, inshallah. Thank you. The certificates, as my colleague Omar said at the start of the webinar, will be sent to you by email within a week. Thank you again. See you soon.
Thank you all. Bye.